Hi everyone, this is week 4 and the last session of the Intro to Stats course. In this session we'll cover inference. Specifically we'll look at distribution test and power analysis. For the session overview we'll cover the topics of t-test, proportion test, power analysis, and we'll use examples from Motor Trend Cars data, the U.S. Department of Health COVID-19 data, and the 1950 Dahlin Hill lung cancer study. Just to review again, the purpose of statistics is first the description of the population or sample, and secondly, inferences from the sample to the population. This includes differences between groups in the population. In the last session we covered sampling distributions and how we do statistical tests in inferential statistics also uses that same sampling distribution. So in the first few sessions we've covered all of the topics that gets us to the point where we can now do statistical tests. And specifically we're going to look at distribution tests. In distribution tests, we can compare two or more distributions of different groups on the same outcome. It does not test causality, but it can help in the Dahlin Hill study that we'll look at later. That's a good example of how some good descriptive statistics paired with useful distribution tests on a very representative sample backed by clinical knowledge or expertise in the subject can really help to prove very important findings. Within distribution tests, we have two types of tests. We have parametric tests, such as a t-test. It uses a sampling distribution and tests whether the difference exceeds a critical value that denotes significance. It's helpful in smaller samples. It resembles the normal distribution when n is greater than 500, when your sample size is greater than 500. It only compares two groups though. And the t-distribution is a little bit narrower in the top and wider in the tails when we're looking at smaller samples, those less than 500. But as your sample size gets bigger, it looks more and more like that normal distribution we've looked at in the past. And for non-parametric tests, we use those such as the binomial proportion test. It does not use a sampling distribution, but it still tests whether the difference exceeds a critical value that denotes significance. So that's a similarity it has with parametric tests. Although it doesn't have a sampling distribution, we use some of the same concepts. Non-parametric tests can compare two or more groups. So we may have different reasons for using distribution tests. Some of the common reasons may be, first, to check to see if two groups have significantly different rates. An example of that is we compare if California and New York differ significantly in COVID death rates. Another reason is to assess if rates of two different years are statistically different. The readmission, for example, the readmission rate in 2021 is better than in 2020. And we can also test a hypothesis. And an example of that is the intervention program reduced CH deaths by 20% as expected. Is it significant? We can all test for this with distribution tests, and when there are other reasons that we can do that, but these are some of the most common. Last week we looked at sampling distributions, and in this slide we're going to cover more on significance tests and sampling distributions. Again, the red circles form the sampling distribution, and so these are the These red circles within this distribution represent summary statistics from an infinite number of samples. And so a summary statistic that we looked at last week would have been the mean. For example, the average age of clinic patients, or we might look at the average length of stay. But the summary statistic of the mean is just one of the values that we can use to form a sampling distribution. What we often look at are group differences, and so we can look at the difference between two groups on their mean rate, and we can collect that value for many samples and then form this sampling distribution that we're looking at here. The white region between the blue is the 95% of the graph area. This is the 95% confidence interval. And last week we discussed that the critical region is that blue area outside of that 95% confidence interval. And these are the things that we'd consider not within our normal range. They're more than just normal variation. These are things that we would want to keep an eye out for. If our study's rare group difference falls into the blue critical region, it's on the left and on the right, that indicates there is at most a 5% chance of being wrong when we say there's a significant difference with these groups. And when we're thinking about group differences in our sampling distribution, each of these red circles represents that difference between two means. So maybe in group A, the average length of stay is 10 days, and in group B, it's 2 days. So the difference between the two would be 8 days. So that value of 8 would fall into this sampling distribution. And if we were to sample an infinite number of groups and see and calculate the group difference between each pair, that's what we'd have in the sampling distribution. But if we have something that's really low, like this red circle in the blue area on the left side, or something very high, like this red circle in the blue area on the right side, if we have something that falls into our blue regions, then we'd say those are significantly different. Everything in this white area represents the normal area. Everything outside of it in the blue area would be our significant differences. A significance test indicates when estimated group differences are not likely to be in the normal range. So we have our confidence intervals, but we also have significance tests, and those are usually represented in terms of probability. Probability of being in the blue region, either above or below our confidence limits. And so some values that you've probably seen are usually the values that look like this. They have the letter P followed by the less than sign, and we have different alpha levels, and those are 0.05, 0.01, and another common value would be 0.001. And these indicate a level of probability that represents something that becomes more and more rare than what we'd see in this normal area. So that P is less than 0.05 value. That would be right about here where this blue area begins. Everything to the right of it would be significant, but right about this point, you only have about maybe 2.5% of the area above it. You'd see that it's denoted by that value of 1.96. We're looking at a z distribution. And if we're doing a z-test, we would use that value of 1.96 or higher to indicate that we have a significant value at the p is less than 0.05 level. And so we have that red arrow pointing to that one point where the blue region begins. And so we have critical values. They're both negative and positive because we're doing a two-tailed test, so we're willing to accept a significant difference that could be either very high or very low. And so that value is 1.96. If you have a very large t-distribution, which looks very similar to this distribution where it's symmetrical and denser in the middle and has less density as you go further away from zero. But a very large sample in a t-distribution would also be about 1.96 in terms of the critical value. So if we move further outside or further away from zero into this blue region, we'd probably see if you get a critical, if your sample mean is if the group differences are stronger, if they're further in the blue region, you might say that it goes to about the 1% area. This is probably not exactly 1%, but this gives us an idea that the further in the blue region we get, the lower the probability of seeing a group difference that large. And so at this point, we'll call it the p is less than 0.01 area. So now we're seeing things that are very rare. So we would say it's significant, but now we can say it's at a greater degree of significance. There's only a 1% chance that we're likely to say something is significant and be wrong about that. And the third value that we see would be the p is less than 0.001 value. And that would be right in the far end of that blue region. There would be very few times we'd see something that high or a group difference that strong. And so we use this to indicate that something's very, very rare. And we'd say there's a 1/10 of 1% chance of seeing something that high, and for us to call it significant and to be wrong about that. So the further we go into this blue region, the more rare it is to see group differences that strong. And we use these p-values to give us an idea of how strong these group differences are. So we know we're in the blue region, but now we know exactly how far we are into that blue region based off this p-value. So that would be the benefit of using the p-values, is that it gives you an idea of how different the group difference that you're looking at, how different is it from something that would say is within the normal range. And because when we look at group differences, the default value that we often use is a 0. So that would equal no difference. So also we have values of 0 for correlation coefficients and regression coefficients. And just to reiterate, we are looking at sampling distributions on group differences. So in these two graphs, they show differences between means in their hypothetical example. A value of 0 would indicate no difference, and 2.83 represents the standard error in that sampling distribution. So so each tick represents 2.83 standard errors from that mean of 0. So we have 1, 2, 3 standard errors listed, and in the graph below it shows the ticks indicated by units of standard errors. So we have 2.83, 5.66, and 8.49, and those can get converted over to 1, 2, and 3 standard errors. And so remember that when you're about 2 standard errors away from the mean, that area above and below the mean is 0, that are 2 standard errors away, represents about 95% of your sampling distribution. So you know beyond that is when you start looking at things that would be considered statistically significant, and you'd have that p-value of less than 0.05. So in summary, we can have sampling distributions on differences in average values between two groups. For example, group 1 minus group 2 equals a difference of 10. That's your group difference. When we examine group differences or correlation or regression coefficients or various other statistics, we often assume the mean is 0 with negative to positive values. So we see it ranges here in the top graph from negative 12 to positive 12. We want to test if our group differences are significantly different from 0, where 0 itself equals no difference. When a test statistic exceeds the critical value, positive or negative, because we can have positive or negative group differences. It depends on which group has the higher value. So group 1 in this example has a higher value, so we end up with after we subtract the value from group 2, we see that it's a positive value of 10. If we switched it around and group 2 had the higher value, or if group 1 had the lower value, we subtract it, then we would be left with the negative 10. But when a test statistic, positive or negative, exceeds the critical value, we have significant results. The difference between group A and group B is 10 points in this example. We know the standard error is 2.83, so we calculate this test statistic as the group difference of 10 divided by the standard error of 2.83, and that equals 3.53. This surpasses the critical value of 1.96. In other words, we have significant results. So a test statistic of 3.53, that would take us to right about where this blue arrow is pointing. And that would be how rare that value is. And when we convert that to a p-value, it'd be less than 0.05. So a related topic when we are looking at distribution tests or in comparing differences in inferential statistics would be power. Power is defined as the probability of obtaining statistical significance and thus rejecting the null hypothesis if the alternative hypothesis is true. In other words, power gives us the probability that we are correct in saying we have significant results. We use it to determine the sample size needed to get power, or the level of power if we already have our sample. For example, we conduct an experiment and find that treatment B is better than treatment A and has a power level of 0.80. If we conduct the same experiment 100 times, we would expect to see significant results in about 80 of the 100 trials. So power gives us a good idea of what's our chance of being right, but also of not being wrong. The suggested power level is 0.80 when we use an alpha level of 0.05. Attaining levels over 0.90 are considered costly in terms of sample size, or it would require very high effect sizes in smaller samples. So at the 80% level, so it's a lot easier to go from a power level of 70% to 80% than it is to go to 80 to 90%. And it's a lot of work and effort to go from 90 to 95%. So we have to really consider when we're thinking about doing a power analysis and trying to attain a certain level. If we do that, it's going to require a lot of our sample, a much bigger sample, or we'd have to feel really confident that we're going to see really big effect sizes. And that's not always easy to see that. In some ways, it's probably still easier to get a bigger sample than to get bigger effect sizes. And bigger effect sizes, what that really is just the difference or the group difference that you see between maybe your treatment group and your control group, or time 1 versus time 2, or some other group difference that you might make. And to help visualize what 80% power looks like, we have two distributions. These are estimated population distributions. The first distribution in red is the distribution of means if the null hypothesis is true. So if the null hypothesis, or your default value, which could be if you're doing an intervention study, it might be the traditional care approach. So if it turns out there is no effect in your intervention group and your performance is similar to the null hypothesis or the traditional form of care, then that's what this distribution will look like. If what's called your alternative hypothesis is true, or in other words, if your treatment group really works or your intervention group really works, then what you're going to be left with is what we'd estimate your population distribution to be something like what we see in this blue dashed line. So you can see that with the bigger the effect size, and that's this horizontal arrow that's up top, the bigger that effect size is, then the bigger the difference in these distributions are, then the more power you have in your results. For example, 80% power of the estimated population distribution of means for treatment B is above the 2.5% level of treatment A. So in this distribution, we see that where that 97.5% of the distribution is where this vertical green line is at. So you can also see how much of overlap you have between the red and blue distribution, and there's probably 20% of this. There's probably 20% of the blue distribution, or our alternative hypothesis, being true. About 20% overlaps with this red distribution. So in fact, about 80% is above that 97.5th percentile in that red distribution. So this 2.5%, that also represents our significance level. So about 2.5%. So this is everything to the right of this green vertical bar is in that would be in that significantly different area. So if you were to just do this, experiment over and over again, about 80% of the values would fall to the right of this green line, and that's for this blue distribution. So if you do this 100 times, about 80 times we would expect 80% of the repeated studies would have values to the right of this green line, and about 20% to the left. So in other words, 80 of the 100 repeated studies would have results similar to what we see in this blue distribution. So that's what power is. You would know the power in seeing your study results repeated in the future. And we might ask what increases power. It's having a higher effect size, which we see in this top horizontal arrow. The bigger the difference between your null hypothesis distribution and your alternative hypothesis distribution, the bigger the difference you have there, then the bigger the effect size. Or another way to look at it is the bigger the difference between your first group and your second group. Another thing that increases power is having higher sample sizes. As we get bigger sample sizes, these distributions become more and more narrow. So if they're more and more narrow, then there's less overlap between the two. And another thing that increases power is to set lower alpha levels, but that's not recommended because if you go with the standard approach of shooting for a level of power of 80%, the standard alpha level that you would use would be 0.05. If you change it to 0.10, then you run the risk of making greater errors or being wrong in your statement. Okay, so we're going to look at examples. We're going to cover t-tests. We're going to use miles per gallon from the motor trend data. We're also going to compare the COVID death rate between California and New York. And we're going to look at proportion tests and power. We'll use the Dahl and Hill smoking and lung cancer study for that. Okay, in this first example, we're looking at miles per gallon, and we're comparing automatic and manual transmissions. So how we would start with any study, we're going to look at some descriptive statistics. For this, we'll look at histograms between automatic and manual transmissions. And just by looking at it, you can kind of see the difference between the two distributions. And we're looking at each sample. So we have our full sample, and now we're looking at subsamples. On the left, we have the automatic transmission. On the right, we have the manual transmission. So with the automatic transmission, we can see that distribution is a little bit tighter. It's a little bit more narrow. It peaks higher, so there's a greater density of cars, probably with their MPG between 15 and probably 17. So we see more concentrated density, and because of that, we see a higher peak in the density itself. In other words, there are more cars that are clustering around an MPG value of probably 13 to 17. And with the manual transmission, we'll see that the miles per gallon rate begins at 15 and spreads to about 35, where the automatic transmission will range from about 15 to about 25. So looks like maybe 5 more gallons in the range. And the automatic, the mean miles per gallon was 17, and for the manual transmission it's 24 miles per gallon. And we see this is a little bit more skewed. We can see with the vertical lines, the black and the red, we have values for our mean and median, and we can see that it's getting pulled to the right a little bit, so somewhat of of a positive skew in this data, but it sort of looks uniform at the same time because almost each bar represents one car, and we have a couple where they have a couple bars where there are two cars with that level. So it kind of spreads. We don't see the same peak in the density, and we have more variation, but we also do have a higher MPG with the manual transmission than we do with the automatic transmission. So in summary, automatic transmissions have a narrower distribution with lower MPGs. Manual transmissions have a wider distribution. So on the right, we have output from a t-test. And we see that on the bottom, we again see the values for the automatic transmission. The average is 17 miles per gallon, and for the manual transmission is 24. So if you were to subtract the two, you'd be left with negative 7.25, and that's the group difference. And what's being done in that calculation is we're now getting a sampling distribution of group differences. So in our sample, we see it's negative 7.25, so we would expect that sampling distribution to have values not too far different from negative 7.25. And the standard error is 1.92. So probably if we were to get two standard errors above and below this group difference of negative 7.25, that's about a value of 4 above and a value of 4 below. So negative 3.25 to maybe negative 11.25. So that's just a rough guess. But below we can see in the 95% confidence interval for group differences, it goes to about negative 11.28 to negative 3.209. So about that level. So from the group difference value and the standard error, we can calculate the test statistic. So before we were talking about 95% confidence intervals on our standard error, based off our standard error. But we can also get a test statistic, and that's calculated as negative 7.25 divided by that standard error of 1.92, and that gives us a test statistic of negative 3.77. And we see that based off of our degrees of freedom, which are 18, because a t-distribution has various critical values for different sample sizes, and that different sample size is represented by the degrees of freedom. We see that we still have a high test statistic that gives us a significant p-value, and that p-value is 0.001374. So this is significant at the p is less than 0.05 level, but it's also significant at the p is less than 0.01 level. So this is something we probably wouldn't see by chance. So let me go back here. That value we just saw is close to that 3.52 value that we had in this graph. So I'll just show you about where that would be in that sampling distribution. So if we were looking at a sampling distribution for these group differences, it'd be at a similar level of something that we'd consider very significant. So it's out here where things began to look significant at that 2 standard error range. And looking at another graph, this is about where our value falls in a graph. Kind of where this big red circle's at right now. Okay, so as I mentioned earlier, we do get a 95% confidence interval for our range of group differences. And it's important to note that the 95% confidence interval for differences in this example does not contain 0. Therefore, we know it is significant. So you'll notice that for this range of differences, they're all negative, meaning that for our groups, we know that the automatic transmissions would have a lower set of miles per gallons. And just to let you know, for the I looked at the data a little bit closer, and I noticed that for the automatic transmissions in this year of Motor Trend data back in the 70s, most of the automatic transmissions had V8s or 8 cylinders, and so a lot of the manual transmissions at that time had 4 cylinders. So in other words, the automatic transmissions had a surprisingly high number of gas guzzlers in it. But this is kind of the standard output you would get. In R, it looks pretty basic, but it gives you the main values. If you are using SAS or Stata or SPSS, you'll get this information, but probably in a neater format. So we'll go on to the next example, and this we're going to look at daily COVID deaths in California and New York for 2020 and the current, and up until about September of 2021. So again, on the left side, we're starting with some descriptive statistics. We're looking at the distributions of California on the left and New York on the right. And we can see that the distributions look different. California has more normality, but both of these distributions are positively skewed. So we can kind of see that by that right tail in California, but we can really see it in New York. We actually do see a high number of deaths. So there must have been one period where they're just getting I think over 2,000 daily deaths. It's hard to believe it was that high, but I think it was. I do think this data is correct. So we do see a lot of values for New York where we have a lot of low values. You can see this distributions. So I'm not sure if they're all consecutive days, but many of the days within 2020 and 2021 for New York where when they had very low values for their daily deaths, but they also have very high values in the thousands, where California doesn't really go beyond 500. But we can just see that these distributions do look different, but they do have some similarities. But New York has a lot of values on the very low end, but also values on the high end. So on the right side, we have the statistical output, and we see that the test statistic t equals 1.64 doesn't exceed the critical value of negative 1.96. So we have a negative value, t-statistic value of negative 1.64, and that's just because if we switched it around where we compared New York to California rather than California to New York, if we subtracted things in the opposite order, we'd have a positive t-statistic. So just to let you know that it's not uncommon to see negative test statistics or positive just by the mere chance of whatever one comes first in that analysis. So we see for California, the mean was about 98 deaths per day, while in New York, over about that 2-year period, it's 125 deaths per day. So they sound different. That's that's close to 30 deaths per day for that difference, but there's probably some variation there. We do see that this is not significant at the p is less than 0.05 level. We might say that it's marginally significant. However, we'd probably want to explore this more to see what's going on with the data. It's not significant at that p is less than 0.05 level, but it's not too far off. Again, we can set our alpha levels at different rates or at different probabilities. 0.05 is kind of the standard approach, but you can adjust it to 0.10, but you'd want to do that before the analysis rather than after getting that value of 0.10. And if you're working with a smaller sample, you might be motivated to do that. With a big sample like this, we would in fact expect to see p-values lower than 0.05, since we know sample size is part of that formula. And the bigger the sample you get, the more likely you are to see p-values that are less than 0.05. So we should investigate this data more. And what we do notice when we look at the 95% confidence intervals for the group differences, we do see that the 95% CI for differences contains 0. Therefore, it is not significant. We get that from the p-value, but we also get that insight from our 95% confidence interval. We see it ranges from -61 to +5, and in between those two numbers we do have a value of 0. So because 0 indicates no difference, our range of likely values does contain the chance that no difference is actually one of the values that represents our population. So if we estimate what the population differences could look like between California and New York, a good possibility would be that there is no difference. But just based off the findings and that they're not that far off from being significant, and the distributions look different enough where we would say that can't be right, we'll go ahead and investigate the data more. And so in this slide, we can show that an exploratory analysis to explain non-significant results can help. So we are now looking at 95% confidence intervals. The one on the left groups all the data from the different months for those 2 years, groups it into one value. And then on the right, now we're looking at that trend over time. So on the left, we see that California has a narrower 95% confidence interval, suggesting more consistency over time. California's average falls within New York's 95% confidence interval. We see that on the bottom, we have New York's confidence interval. On the top, we have California's confidence interval. And this little blue dot represents the mean for California. So if we were to move our cursor down, we see that it falls within that red band, which represents the normal range for New York. So we already know that these are not significant, but this gives us an idea of there being a greater consistency in those average daily death values for California, where we look at New York, and we kind of saw that with the histograms that we looked at in the last slide. but we do see a pretty wide um, confidence interval, which represents a lot of variation. And we see that mean is right here, about 125. But we do see a big spread. So what could be a normal value for New York could be between 92 to about 158 days, or 158 deaths per day. So that's a pretty big difference. We do know time, there is a big time effect for COVID. Things have changed since the very start back in 2020. So it's useful to see what that trend is over time. Time is important in understanding differences in average daily COVID death rates. California and New York had significantly alternating levels over time. And we see that on the right side. We see that California and New York's 95% confidence interval shows they have significantly different rates over time. New York's rate has the highest variation, but California finishes with a higher rate. So in this purple band, we see that it's New York's confidence interval, and in the blue band, we see California's rate with its confidence interval. So we see in the beginning, the average daily deaths was really high in New York. I'm using the smoothed trend lines. The rates for the actual numbers go up and down, and it's just kind of harder to understand what's going on visually. So I'm using the smooth trends just to give me a general idea. But we see for New York, it started out at really high levels back in March. There was some improvement over time, but it took a number of months before they started to see things come down. They did see it towards the end of 2020, and they've maintained a certain level since then. For California, it's slowly gone up. It slowly went up in 2020, peaked around January of 2021, and you can see with this wider band in the winter months, you can guess. I'm looking at a smooth trend, but I can guess because of this greater variation represented by that wider blue band. We could guess that it went up and down for those months. And we know the winter months were bad here in California, but we can see over time the death rate's gone down. You also have a vaccine that got introduced in big numbers in the U.S. in the new year in 2021. So we also are starting to see death rates go down in both California and New York. But for California, we do have the highest rate. And so these are so what this example shows you is that you begin the process by analyzing your data. You do some descriptive analysis to give you a good idea about your single sample. Then you do statistical tests with and you also get confidence intervals on values that make up your sampling distribution, and that sampling distribution gives you a p-value, and that's the result from a distribution test, and that's what we're doing here. We're doing a t-test to compare California and New York. We didn't see significant findings, but we did notice that there was something a little bit off based on our understanding of our descriptive statistics. So what we went ahead and did was an exploratory analysis, and that gave us a better idea of what's going on, and now we can understand the results better and explain it to our clients. And so now this last example is the 1950 smoking and lung cancer study by Dahl and Hill. And this is a non-parametric test, so we don't have a sampling distribution in the traditional sense, but we do use a test statistic, which is this chi-square value. And we can still use that to find a significance level. We have a p-value of 0.000002057, which is very significant. And we do see that we have a 95% confidence interval on our group difference. And the 95% confidence interval doesn't contain 0, so we know it's another way that shows us that this is a significant result. That range of differences in a hypothetical, that range of differences would be between negative 0.35 and negative 0.14. And so that would be the group difference between non-smokers that had lung cancer, and this should read as 51% of smokers. But we see that when we're looking at those who smoked and those who had lung cancer, the rate is about double for smokers. And so this was a sample in which there were about 1,400 patients at a hospital. They identified 709 that were smokers and had that 709 patients with lung cancer and another 709 who didn't have lung cancer. There were high numbers of smokers in both groups, but when we looked at those who had, or when they looked at those who had cancer, 51% of the smokers had lung cancer, while only about 26% of the non-smokers had lung cancer. So the rate was more than double. But at this time, their competing hypothesis was that lung cancer was increased by car pollution. The same kind of car pollution that we discussed today, but they thought of that as being a cause for cancer, lung cancer. I think there was only maybe one other study that examined the effect of smoking on lung cancer. So they did a distribution test, but they didn't. It wasn't the traditional causal form, but 1950 didn't have a lot of computing power. They did a good job in sampling. They matched up things between both groups on age, sex, and the location of where these people were at. So they did some pretty solid work, and they used a distribution test. And from that point on, we did have proof that there was a link between smoking and lung cancer. And so just to cover power analysis, I entered the rates of 0.2625 and 0.514 for both the groups, and I chose an alpha level or a significance level of 0.05, and I calculated the level of power, and that's 1, which indicates there's 100% power in this analysis. I did something called an effect size. I calculated that to be about 0.52, which is a medium effect size. And effect sizes are helpful because they don't rely on sample size. So you can have a very large sample or a very small sample, but you can get the same effect size both times if the difference between the two groups is big enough. Because of the large difference in rates between smokers and non-smokers and the big sample, power equals 100%. It is important to note that this is a post hoc power analysis. A power analysis should be done prior to the study start. However, this distribution test revealed important results in public health. So you can still find important results through these types of analyses. What you've just looked at was the entire set of statistical tools and concepts that we've looked at in the last 4 weeks, and this is the process that we would go through using our starting with our descriptive statistics and using a variety of inferential statistics to help us make meaningful conclusions. Thank you.